This problem involves rotation, but it asks about a tire which is attached to a car. So it's about a car tire, T-I-R-E, or T-Y-R-E as they spell in Australia. This car is sort of going down the road with a speed here of something like 20 meters per second. So if the car is going at 20 meters per second, the wheel is also going at 20 meters per second because the whole thing is attached and sort of going down the road that way. So that means that the center of mass of the wheel here is also traveling down the road at 20 meters per second, something like that. So what they want to know then is if this wheel is traveling at 20 meters per second, how fast is it rotating? In other words, what is the rotational speed of the wheel here, the omega of the wheel, given that it has a diameter, as stated here, of 0.6 meters. So you have this wheel which has a 0.6 meter diameter, and they want to know how fast it would be rotating if it also had to move at 20 meters per second. So the relationship is actually pretty simple. It's actually a really subtle one. There's lots to talk about, which we'll probably talk about in class or perhaps on another video or something like that. But in particular, omega here is always known to be V over R. That's just something you should just know or get in your head. The relationship between linear speed and angular speed, something like that. It's always sort of moderated by the R in there. And so the problem, this answer pops out pretty quickly, but we'll have just a bit more to say about it. So if you just divide the 20 meters per second divided by the radius, the 0.6 meters right there, you can go ahead and get your omega for the car here. Just put that number in your calculator and you'll get it. Sorry, not the omega of the car, the omega of the tire. So not a very difficult problem. But let's talk a little bit about the ramifications or the meaning of that particular equation right there, because there's something kind of interesting about it. Okay, so we'll look at it this way. You got to answer the problem, but here's a bit more on what all this stuff means. Suppose you had two cars then. So we'll draw a really big car, maybe like a big Ford Excursion or a big truck or something like that, sort of traveling down the road like this. It has these really big wheels on it like that. And then right next to that big car, say it's going at the same speed, you put a little Honda Fit, which has these little bitty toy wheels like this. Sort of looks like this. My car is just awful, I know. But there's two cars. The only difference between them is the size of the car. Okay? So these cars here, this car here, say, is moving some speed down the highway. Maybe we'll put a big V on it. Let's just use some good old lame American units, 55 miles per hour, and say this one's also going at 55 miles per hour. Okay? So the cars are traveling at the same speed. One is not going to overtake the other. If it was window to window, you could literally drive up next to one another and shake hands or throw cell phones between the cars, whatever. They are traveling at the same speed. But the question then is, okay, they're traveling at the same speed. What are the wheels doing then? How are the wheels behaving here? And let's say we look at this car right here and say these radius have some radius R1 right here, and these little bitty wheels in here on the smaller car have their radius too, but we'll call it R2, something like that. So the question is, the cars are traveling at the same speed, but what is the rotational speed of the wheels then? So what are the omega of these wheels right here, omega 1, and what would the omega 2b of the wheels down here on the smaller car? Well, that's where the relationship comes in, because it turns out that a smaller wheel has to spin faster to keep up with this speed right here. And you can just sort of imagine that. Here's the big car lumbering along. You can imagine that the wheels are sort of rotating and rotating and rotating, sort of a nice easy pace to keep up with the 55 miles per hour because you don't want any skidding or slipping. Where down here, if you get this little car to go at 55 miles per hour, these little wheels in here have to go like zzz, just spin really, really quickly, sort of to keep up with the car. So the wheels, although the cars are traveling at the same speed, the wheels are not spinning at the same rotational speed because their radii are different. And so that is sort of the ramification of this equation right here. V omega is equal to V over R. You go, look, okay, if you want to get a wheel to travel at so much speed, so fast, like 55 miles per hour, and the wheel has a given radius, this tells you how fast that wheel better rotate to keep up with the required speed that you need right here. So like in the big car right here, we'll have omega 1, which is the 55 miles per hour, and we'll divide by the big old R1 right here because it's a really big car. So what that's going to tell me here is the omega 1 is going to be relatively small. Because R is such a big number in the bottom of the 55, omega 1 will be sort of a small number. But now if I come over here and look at the smaller car, the omega 2 for the smaller car, it's going to be the 55 miles per hour. But now the R2 is incredibly small for that car. It has these little bitty wheels on it. So what that means here is omega 2 is going to be comparably large. That's the way these two things are going to compare. Now, I don't know what the actual numbers are. You can go measure wheel diameters of, say, a Ford Excursion and a Honda Fit, and if you get them up on the highway at 55 miles per hour, as you can see just from this simple analysis right here, the big wheels on the big truck or the big Ford right there don't have to spin as fast to keep up at 55 miles per hour as the little wheels do on the Honda Fit. These things have to zip along, because the radius is so small. This is a larger fraction. The angular speed is going to be relatively large for the Honda Fit, relatively low for the big Ford Excursion. So now you can begin your arguments that for the same amount of driving, the Honda Fit tires, say, need to rotate much more than the Ford Excursion tires do, and you can start talking about tire wear and that sort of things. But that would be the difference then between a big car and a small car. These tires have to spin very quickly, very fast Omega to keep up with the 55. These can lumber along at a slower rotational speed. So this equation here, as simple as it is, and as easy as this problem was, actually has some kind of interesting dynamics about what you would see or what it would be required to get something to spin while it maintains a certain linear speed. Nice equation in there.